sample means with t-distribution. So, why do we want to have a large sample? As long as the observations are independent and the population distribution is not extremely skewed, a large sample ensures that the sampling distribution of the mean is nearly normal. The estimate of the standard error as s over the square root of n is reliable, and that the estimate as s over the square root of n is reliable. Our estimate of s, right, our s as an estimate for the population standard deviation, right, s being the sample standard deviation. If our population is 100 observations and we sample 99 of them, our standard deviation of that sample of 99 is likely to be very similar to the standard deviation of all 100. If we sample 90 of them, the standard deviation S of that sample likely to be pretty close to the population standard deviation. If we sample 3 of them, the standard deviation may be very different, right? So if the population looks like this, if we have a small sample size, we get this one, and this one, we're going to have a much larger standard deviation. Whereas we could also get, this one, and this one, and have a much smaller standard deviation. So, the larger our n is, that means that our sample standard deviation is closer to our population standard deviation, which makes s over the square root of n closer to sigma over the square root of n, which would be the standard error in the ideal world where we know the population standard deviation, which we usually don't. Central limit theorem states that sampling distributions will be nearly normal, which holds true for any sample size as long as the population distribution is nearly normal. If your population is approximately normal, you meet the normality condition automatically, which is really handy, but it's very rare that we know that the population distribution is nearly normal in the real world. You may have examples that tell you to assume that the population is approximately normal, and that's awesome. But in the real world, we rarely know that. And it's inherently difficult for small data sets. If you only have, a sample size of 10, we may not be able to see normality. So, not just examine the data, but think about where the data come from. All right, would I expect this distribution to be symmetric? Am I confident that outliers are rare? Right? A distribution of the height of, Americans, probably approximately symmetric, right? We have a lot of people around average height, and you have some very short people and some very tall people. I would expect that distribution to be symmetric. The distribution that we saw in our example of the income that people earn from making YouTube videos, I would not expect that distribution to be symmetric. I would expect it to be skewed right with quite a few high outliers. So, just something to think about. Would it make sense for this distribution to be symmetric, to have as many outliers on the high end as the low end, and for those outliers to be relatively rare? So, our conditions for inference for a t-interval: simple random sample, Normality, which we can meet by one of these three things. Either your population distribution is normal and your n can be any size. Population distribution is unknown, but your n is at least 30, assuming the population is not extremely skewed, but again, keyword here being extremely, you probably don't have to worry about this one. If your n is at least 30, you can be pretty safe applying the central limit theorem. As a last resort, if we don't know the population distribution and our n is less than 30, we can look at the sample and see if the sample shows strong skew or outliers. If there's no strong skew or outliers, then we can assume that the population distribution is fairly symmetric, or it's fairly symmetric, and proceed as if it were normal. And then our last condition is independence, the key part being that the sample is less than 10% of the population. When we're working with small samples and the population standard deviation is unknown, which is pretty much always, the uncertainty of the standard error estimate is addressed by using a new distribution, the t-distribution, instead of the normal distribution. T-distribution is also bell-shaped. It looks very similar to the normal distribution, but the tails are thicker than the normal distribution. So observations are more likely to fall beyond 2 standard deviations from the mean. These extra thick tails give us account for the less reliable estimate of the standard error. When our n is small, our s is going to be a less accurate or less precise estimate of the sigma, the standard deviation of the entire population. And so to account for that additional uncertainty, the extra thick tails in the t-distribution help for that. Right, so the red here is the normal distribution, the blue is the t-distribution with some degree of freedom. But you can see that the blue is taller here, the tails are thicker. More of the data are in the tails. T-distribution is always centered at 0, like a standard normal distribution. The normal distribution has 2 parameters, a mean and a standard deviation. The t-distribution, the mean is always 0, so that's not a parameter. The parameter of the t-distribution is called degrees of freedom. For one sample t interval, your degrees of freedom are equal to n minus 1. And so you can see that as your degrees of freedom increase, your tails get thinner and your median gets taller and it approaches a normal distribution, right? This one here has the lowest degree of freedom, 1 degree of freedom. And then as you get more degrees of freedom, you increase here and you decrease here, and you get something that resembles a normal distribution. And so a t-distribution with an infinite number of degrees of freedom is a normal distribution. This is a t-distribution table, a t-table. And so the t-table is organized according to degrees of freedom. And then it's going to tell you inside each cell is the number of standard deviation, the number of standard deviations that you need to go in order to encompass a certain percentage of that data, right? And so the table here is showing you this shaded part is what what each of these numbers refer to. So if I was doing a 95% confidence interval, right, I want 95% of my data in the middle, I want 2.5% in each tail. So I'd be looking at this column with the 0.025. It's going to tell me that there's 0.025 of the data in that upper tail. And so how many standard deviations do you need to go away from the mean in order to get 0.025 of your data in that upper tail? And also in the lower tail, it's symmetric. If you only have 1 degree of freedom, that's a staggering 12.7 standard deviations away from the mean, which is a lot. If you've got 2 degrees of freedom, that drops down to 4.2, and you can see as you go down the table, your number of standard deviations, your critical value, gets closer and closer to about 2, right? And at the infinite level, right, with an infinite number of degrees of freedom, you get, instead of the t-score, you get the z-score, which would be 1.96. So, as your number of degrees of freedom get higher, you're going to approach, in this case, 1.96 as your critical value. It approaches the z. And usually your t-table is going to stop at like 30 or 50 or something. Because if you have more than that, you could just use the z. For our purposes, we're going to use t all the time for a mean, even if we don't, even if our n is large, even if your n's like 100, because you're not going to be using this table. Like, let's be realistic. You're going to be using your calculator, and your calculator can give you the critical value for any number of degrees of freedom. So we might as well just use that, and if it's big enough to be approximately normal, your calculator will just give you the approximately normal value. So we're going to use the t all the time. We're not going to worry about when you can use t, when you need to use t versus when you need to use z. With one exception, but I'll get back to that later. Alright, so confidence intervals, always in the form of the point estimate plus or minus the margin of error. Margin of error is always the critical value times the standard error. For a sample mean, we're going to use t as our critical value instead of z. And then our standard error here is s over the square root of n. Alright, so a 95% confidence interval for a population mean based on these data, we would need to first find the sample mean and standard deviation. And so what you can do is you can put all of these into a list on your calculator and then go to one variable statistics, and it will give you the mean and the standard deviation. If you need an demonstration of how to do that, come see me in class or before or after class, and I can show you how to do it. But you'd put all these into your calculator, and the calculator will give you the mean and the standard deviation. You could also calculate those by hand, but the standard deviation in particular is a pain to do by hand. So, anyways. So you get the mean and the standard deviation. You also need, if we want a 95% confidence interval, you need a t value. So 95% confidence corresponds to the 0.025 in each tail. We have 5 values here. So our n is equal to 5, which means that our degrees of freedom is n minus 1, which is 4. So we're going to look at row 4 on this table, and we would use this t value. Or you can do the inverse t function on your calculator and you put in the area and the degrees of freedom. So you would do inverse t, your area is 0.025, your degrees of freedom is 4, and it's going to spit out exactly this. These tables are what we used in ye olden days before everybody had calculators. On the AP test, though, you always get to use your calculator, so you might as well. There's no non-calculator portion, so I honestly don't really see the point of making you use a distribution table. So that's going to give us a t value of 2.78, thereabouts. And then we apply the formula, right? So your confidence interval is equal to your point estimate plus or minus your margin of error. Point estimate is 51.816. Your margin of error is the t critical value times s over the square root of n. So this is going to be 2.776 times 11.437 over the square root of 5. 11.437 over the square root of 5. And multiply that by 2.776. And I come up with a margin of error of 14.20. 199. And so then you would add that and subtract that and get your confidence interval. And I might as well while I'm here. 51.816 minus 14.199 gives me 37.617. And 66.015. There you go. There's your confidence interval. Ms. Schumann randomly samples 6 pre-calc students. She finds the average grade is an 88.6 and the standard deviation is 6.11. Construct a 95% confidence interval for the average grade of Ms. Schumann's pre-calc students. Assume all conditions are met. Because I can tell you already this fails the 10% condition. But assume that all conditions are met. We're going to do our 4-step procedure. So state the parameter, which is the average grade of Ms. Schumann's pre-calc students. That's the parameter. And the confidence level, which is 95%. We name the test. This is a 1 sample t interval for mu. And we check the conditions. You should check all the conditions, but we're just gonna, in the interest of time, we're just gonna say that all these conditions are met. Our general formula is the point estimate plus or minus the margin of error. The specific formula is going to be x bar plus or minus t star times s over the square root of n. You are going to need, and then we plug in the numbers. So x bar is 88.6. We're going to need, we've got 5 degrees of freedom this time. So for a 95% confidence interval, that's a t-value of 2.57. Times, what did I say, S was 6.11 over the square root of 6. So 2.57 times 6.11 over the square root of 6. Is 6.41. Right, so that's going to be 82.19 and 95.01. I just did that math right in my head. And then your conclusion. We are 95% confident that the interval from 82.19 to 95.01 captures the true mean grade of Ms. Schumann's pre-calc students. There we go. That's the full procedure. Ms. Manaker wants to know the average spring high temperature in Atlanta. She randomly samples 8 days between March 22nd and June 21st and records the highs for those days. She gets an average of 70.5 and a standard deviation of 7.2. Construct a 98% confidence interval for the average spring high temperature in Atlanta. So, our parameter is the average spring high temperature in Atlanta. Our confidence level is 98%. We're going to assume the conditions are met here, but random says that she randomly samples. We do not meet the 10, we do not, because these are all sampled from the same year. This would actually, our population could only be generalized to 1 year. So if our parameter is the average spring high temperature in Atlanta for all time, that's not going to work. But 10%, 8 is not less than 10% of all. Yeah, it is. There's more than 80 days in spring. There's 90 days in spring. So yeah, sure, we meet the 10% condition. Less than 10% of all spring days. That'll work. And we're going to assume that the distribution is not extremely skewed. We don't know that our population is normal. We don't have an n greater than 30, so assume sample is not extremely skewed. Theoretically, you should have the actual data and you should check that, but we don't for this problem. So, and I forgot to name the test. It's a 1 sample t interval for mu. And then we list our general formula, which is the point estimate plus or minus the margin of error. Our specific formula is x bar plus or minus t times the s over the square root of n. Our x bar is 70.5. For a 98% confidence interval, let's go back to this table here. Our n is equal to, come on, give me my table back. There we go. Right, our n was equal to 8, so our degrees of freedom is going to be 7. And for a 98% confidence interval, it actually in this table handily tells you here, but we want to be looking for the 0.01 in each tail. So we're looking in this column, we're looking for 7 degrees of freedom. We're going to be, our t-value is 2.998. So 2.998, our S was 7.2, and over the square root of 8. 2.998 times 7.2 over the square root of 8 gives us a margin of error of 7.632. So our confidence interval is going to be from 62.868 to 78.132. And then our conclusion, we are 98% confident that the interval from 62.868 degrees Fahrenheit, presumably, doesn't actually say that, but to 78.132 degrees captures the true average spring high temperature in Atlanta. There we go. This is something different. We'll save that.